All right, welcome. So today we're going to carry on the exam review. So this is the second section for it, and then we're going to continue on with additional exam review on Monday. So Wednesday will be your exam in the Engman lab. So normal class time. Topics again are these. Last time we focused mostly on identifying op-amps, and then we went into analyzing op-amps. And today we're going to do another analyzing the op-amp configuration, finding the output voltage based on the configuration, and then we're going to look at creating an op-amp circuit, and then looking at combinatorial circuits. So at the end of today, please also make requests as far as other additional types of problems you would like to keep reviewing. And then we'll focus on that on Monday. So I will take requests of anybody that's not here that wants to also email me for specific topics for Monday. Please let me know. Or if you don't want to say out loud, just anonymously, let me know. Okay. All right, so this circuit, want to find the output expression for V out. So V out will be an expression such as VO is equal to A times V1 plus B times V2. So finding A and B. So go ahead and work on this for a minute and see if you can get that expression. All right, what's this first op amp on this one, on the top? Okay. Non-inverting, good. This one? Thank you, inverting. And this one? Correct, subtracting or difference. All right, so for the non-inverting, the gain of this one is going to be at this output node is going to be R1 over 1K, so R1 over this one, so that resistor over that resistor plus 1. And R1 was 9K. Let's write that. So 9K over 1K times V1. So what's going on with this 1K? It's not affecting it at all, right? So not affecting it. So you have to notice that in this, that's not going to affect the output. So this is 9V1 at that wire. So this whole wire. And again, that acts as the characteristic of the op amp. It acts like a voltage source there, fixing it at 9V1. Yes. Yeah, sorry. Thank you. I've been a little off the last couple days, so. Okay, plus 1 in there. So yes, 10. Please watch my math today. It's a little off. Okay, 10V1. So 10V1 at this wire, and that's fixing it like a voltage source value. So it's not going to change the voltage no matter what other resistor you put there. So I could put another resistor, and this resistor doesn't affect the gain at all either. Okay. All right, yes, question?
My question was just, is the one you're adding on, is that because we're in kilo ohms for the resistors? Like if we were just in ohms, would it be like you're adding 1,000 or?
No, the plus 1, so you can write this either way. You can say it's this resistor over this resistor. So let me write it both ways. So writing it can be the R1 over 1K. Well, I'll call this RX and this RY. So it's the location of these resistors or what's going to be the main one. So you can write it like this, or you can write it as RX plus RY over RY. So they're the same thing. I just typically like to write the top one. So you can write it either way, but when you do the analysis, it ended up being those specific resistors are in the ratio of the RX over RY. Does that make sense? Okay, other questions? Comments? Okay, let's look at the inverting one. So in the inverting one, it's going to be this resistance over this resistance and a negative. So negative, and R2 in this case is 4K, so negative 4K over 1K times V2. So a negative 4 V2 is going to be the fixed value at this wire. What if I add an R4 there? Okay, good. It does not affect the gain at all. So this would be another resistor you would basically ignore. Okay, now going into the subtracting or difference amplifier, we now have these two that are acting as inputs into the subtracting difference amplifier. So the subtracting difference, on the negative side, it's going to be an inverting gain, so that output is going to be that portion of it is going to be the R3 over 1K, and again a negative. So it's a, R3 is 5K, so 5K, or negative 5K, over 1K, times the input for this one, which is minus 4V2. And then you have to add the other side, which is going to be an inverting portion that also has a voltage division between these two. So with these being equal, that division is going to be exactly half. So at this wire, you're going to have 10V1 times, R3 was 5K, over 5K plus 5K. And that will be exactly a half of that. So going into this one is going to be 5V1, and then it's a non-inverting portion, so it's going to be the 5K over 1K plus 1 times that input, which is 5V1. So this ends up being minus 5 times minus 4, so plus 20V2. And then 6 times 5 is 30 V1. So this would be the answer, yes.
Would you recommend, because on the table with all the equations you gave us,
Mhm.
it kind of told us to do the gain before multiplying it, like the total gain of the plus before multiplying it by b. Would you recommend that, or would you recommend the?
Oh, I don't have it on this one.
Because what you did is you multiplied like the second part of the gain. What would be easier in the future?
So I like to look at this subtracting difference amplifier by doing the superposition of that one. It's easier for me to visualize that than trying to write out the whole equation and then figure out where the resistors are. So it's personal preference of which one you like to do first. So I incorporated this one, and then I used that as my input signal into this portion, which is the non-inverting portion.
Oh, okay.
So-
it's the voltage divider in front of it, and then
Yeah.
you do the second.
Yep, so this is the division, the voltage divider portion.
So it's just purely personal preference.
Yeah, so last time you saw the example we had didn't have a voltage divider there. You already knew what the voltage was. And so you have to kind of understand that concept and that where this is kind of derived, so
Because the
that,
voltage, you did it because the voltage divider comes before the op-amp.
yeah.
Okay.
So I just decided to do it then, but you could have wrote this whole equation and then figured out where those resistors are based on matching it to this circuit. So your, personal preference of what you feel is easier for you to understand. All right, any other questions about achieving this and answer?
So I had a question about where you did the 10V times the 5K over, the 5K plus the 5K.
Mhm.
Is that based if that point is on that diagram, or is it if that, resistor is going down?
So the red wire at the top has to stay fixed because that's a voltage source. So it doesn't matter whatever resistors you put there. The R3 and then the other R3 going down creates a division, so the node on the other side is going to be a different voltage value. So you can either figure it out by node voltage there, or you can figure it out knowing like, oh, I identify that that's a voltage divider and doing it then. Does that make sense? So it does depend on where the location of those resistors are, whether it's a divider or not. Okay. What if I put a resistor here? Oops. If I can draw. What if I put an R4 resistor there? Does it do anything? Okay, good. Nope. That would be another one you could ignore.
Because there's no current going into the.
Correct. Yep, no current flowing into there. What does the 7K at the V out node do? If I increase that 7K to 10K. Okay, good. Seeing good. No change at all. So again, that's another one that's ignored. So if it changes, it doesn't affect it. What if I increased R2 here? What change would that have? Correct. So this would be a larger, instead of -4, it would be whatever increase it had. So you'd have a more negative portion there. In the overall, what would that do? Would it increase or decrease the overall V out gain? It would increase it because that ended up being a negative and a negative for a positive. So that would increase it on your output. So that would increase your output too. All right. Yes.
Can you refresh kind of on a couple of the rules of determining when a resistor will not have any effect on the voltage within an op-amp configuration like this?
So that a lot of that is understanding the derivation of how the equations get
So look at
derived.
the equation and then just say, okay, if it does, it won't have any.
Yeah, that's not in the circuit configuration. It's not going to have any effect. Some of the other things, like if I put a resistor in parallel, so what would happen here if I put another R3 there?
I mean, you probably have to include that in the equation, yeah.
Correct?
And
So that would affect it, right?
Yeah.
Because it would change then that voltage division, and you would actually have more than just half. It would be more than 5V1. It would be an increased value there. So with that, you have to see, yeah, it will affect it somewhere. So this one will affect it. And then all the others that are marked are going to affect it, except for this one K. Again, it's the same as the top one. It wouldn't have an effect.
So with the extra resistor that's parallel with R3 that you wrote,
Uh-huh.
to get the two values for that, would you just do two individual voltage divider equations and then combine them, or would it be just the same because they're parallel?
So I would put them in parallel and then use that in the voltage divider equation.
So basically, if we have like extra resistors that would change the voltage, do we just need to get like a equivalent resistance into like the simplified circuit
Mhm.
that kind of matches the op-amp configuration?
Correct,
that's on
yeah.
there?
Correct. And then if you know, like here, like looking at just R2, you already know the equation, so you would look at the effect based on the equation itself. All right, any other questions? Okay, I thought this would be another good exercise to go through this one and mark the resistors here that are gonna, that could be removed from the circuit without changing V out. So the ones that are gonna have an actual effect on the magnitude. So take a second and then we'll go through the solution for that one. Okay, what about this one? Do you need it? So yes, we need that one. This one? Correct, we can remove that one. What about this one? So we need that one.
Wait, do you need the green one or the one with the blue check? Sorry, blue check, not blue. Circles are green, right?
Blue check is that you need it, and then the green is, could be removed. All right, what about this one down here?
Remove.
Okay, remove, good. Oops. What about this one? Okay, that one I'm getting a couple funny looks. So this one is one we haven't talked about, but remember this has to be a fixed voltage at this node. So that resistor is not gonna affect that because it's gonna be that fixed VO value. So when you do the analysis, we know that we need enough current coming from there to create that node to stay at V naught. So the resistor is not gonna make a difference there. So that one could be removed. Yes.
So what if it was a switch comparator? Would it still be the same?
Uh-huh.
Oh, okay.
So if it's a switch and you had a resistor there, it's gonna be either whatever the supply voltage is. So if I had a 9-volt battery, it would be 9 volts or a minus 9 volts if I had a plus and minus 9 volts. So it's still gonna fix it there. And if I added in, a resistor with a LED to light it up, that would still stay fixed even with the switched comparator. So that voltage still stays the same. All right, what about this one? Yes, you need that one. That's part of the subtracting and inverting side. So this one is needed. This one? Okay, good. You can remove that one. What about this one?
Yes.
Yes, you need. Okay, what about this one? You need because that's creating a divider with this one, correct? So you need both of those. Otherwise, your signal would be different. What about this one? No. Yes.
About that second one in the divider without the cell, can't you remove it because there's no voltage going across, and so V2 is 0, and it wouldn't make a difference either way.
So the voltage at this node is going to be different if I removed either of, I'll call them R1 and R2.
The right one specifically.
So this R2 one?
Yes.
So if you remove the R2, then there's no current going through R1, and this red one would be 5 volts, which is different than if I have R1 and R2, because the voltage here is going to be the divider, be -5 times R2 over R1 plus R2. So there's current going through here, and there's current going through here. There's no current here. But because there's current going through those other two, I1 and I2, that node will not be 5 volts, but if you removed one of them, it would be 5 volts. So that is a change in that voltage. Does that make more sense? Okay. Other questions? Okay, what about this one?
No.
Correct. So we can remove this one. Oops. Green. All right, what about this one? Just the way it is, it could be removed. Because it's floating, there's no current floating through there. But if I actually put this on the output and put my V out here, this node here would stay the same as far as the output of that subtracting, and then it would go through, then it would go through a divider, so Vx. So this one would need both of these to not change the output, but this one is basically just floating there, so it could be removed. And then VO in this case is equal to the Vx. Does that make sense? Yes.
Why would removing either R1 or R2, as we were talking about earlier, why would removing one of them make it so there's no recurrence?
So if I removed R1, it would look like this. There would still be current flow in here, but it would be 5 over R2. Because the 5 volts would fix this, the wire there. Does that make sense? So there's still current there. It just is going to be different than having R1 and R2. And the voltage at that node will be different. If I removed R2, that circuit would look like this. Go in the positive side. And now there's no current flowing through it because it's all,
Oh, because, okay, you removed the other path.
yeah. So the voltage here again would be 5 volts.
And then,
So that's why you can't remove either one. Does that make sense?
but if it's just R2 wouldn't matter.
For the 5 in the parallel with R2, or what do you mean?
Yeah, or no, okay, yes, because then it would be fixed, okay.
Yeah, because this one has a fixed value there from the voltage divider, which is different than, oh, I wrote these upside down, sorry, but anyway, same idea. Put a minus plus. So this would be minus 5 volts, and this would be a minus 5 volts, which is different than minus 5 times R2 over R1 plus R2. Okay. All right, other questions? Okay. All right. What I have. Do you guys want to work on designing an op-amp system or moving to combinatorial review? I'm saying please this one, yes. Okay, so let's work on this one.
Be on the exam.
It could be yes. Okay. So with designing an op-amp system, so you get a mathematical expression, you then want to say, like, how can I even create this? Okay, so you see that there's a subtraction, so you're probably like, a subtractor needs to probably be in there, is one thought. So then you want to see, can I create a subtractor so having this opposite of signs leads you to think like maybe a subtracting difference amplifier. So then the question is, can I just do that with one subtracting circuit and use the resistors to create a 1/3 for the V1 and a 7, which would be a subtracting on the V2 side. So thinking back about the subtractor, go grab it. So with this, is there a way to create, we need a -7. So an R2 over R1 would need to be 7 as far as a ratio. And at the same time, if R2 over R1 is 7, is there a way to create R3 plus R4, or R4 over R3 plus R4 to be, it would need to be 1 over 8 times 3, correct? So it would cancel out the 8 and give us a 1/3 of that input signal. So is there a way to create R4 and R3 plus R4 to be 8 times 3 is 24?
R4 could be 1 and R3 could be 23, right?
Okay. So R4 could be 1K and R3 being 23K. The reason I use K is because if you use ohms and use really small values, usually when you have currents that are drawing through them, that's going to be so small it will heat up. And so typically in designs, you want them to be in the K range when you do a design. So that's why I'm always putting down like 1K instead of 1 or 10 or 100, because 1's easier to divide by 2. Okay, so this would give 1K on the top and then 24K on the bottom. Multiplying that by 8, that would give you that result, correct? So then what could you do for R2 and R1?
You could do like, we were kind of screwing around, but we did like, R2 is, R2 is 21,000 and R1 is 3,000.
Okay, that would work, or not, okay, 21,000,
We were feeling so close.
and R1 is 3,000, okay. Any ratio that gives you 7 is gonna work there, so you pick one and then you get the other one. I like 1K because it's easy to multiply by, so I would probably have picked the bottom one to be 1K and then just put 7K on the top. But any ratio that gives you 7. So now we can just go put these in. So if we have, so we also need to decide what signal goes on which line. So R1 we had is 3K here, 21K. R4 was 1K and 23K. And is this correct for the V1 on the top and V2 on the bottom?
No. Yes.
Correct. So I need the 1/3, which is the non-inverting portion side, to be of the V1 signal, and this one to be the V2 signal. So there's your design. So sometimes you can't find a ratio to give you something like this. So in those cases, you may need to do multiple op amps. So you may want to reduce one signal and then being able to amplify it together. But this one works for this one with one amplifier. All right, questions? Actually, we do have time to go into the digital logic one. give you guys a second though to write this. Okay, so for this one, fill in the truth table for the X and the Y. And then decide what goes in the question mark box to create the Z output. So take a minute to work on this one. Okay, so hopefully you were able to recognize this was a NAND gate. So whenever and this is an XOR, whenever the inputs are the same or are 1, 1, you get a 1 out of an AND gate, so you get a 0 out when you have a NAND gate. Everywhere else it's going to be a 0, which the NAND portion will flip into a 1. So you have all 1s except for the last 2 where A and B are 0s. For Y, it's an XOR gate, and so with that one, your inputs are B and C, so whenever they're the same, you have 0 out, and when they're opposite, you get a 1 out. So that would leave with that one. So what do you have for Z? Okay, an AND gate, let's check. So an AND gate, a NAND gate, okay. A NAND gate, you would have 1, 0. So everywhere you have opposites or 0, 0, you're gonna get a 1 out, and then only when you have 1, 1 will you get a 0 out. So you can see that those are actually true. So yes, a NAND gate would work there. All right, we don't have time today, but this is kind of a fun little thing. If you guys want to look on it on your own, is to create a binary codes to be able to turn on a number on a 7-segment display. So on this, you can see the A, which would be this little LED light. To turn that on, you're going to want that on when it's a 0, when it's a 2, when it's a 3, when it's a 5, 6, 7, 8, 9. So all of those would have those ones in there. So you could create the truth table for each segment of the display, and then you can create logic from it. You can reduce down the logic a little bit by noticing that terms. So if you look at these two terms together, you notice that the only difference between these two terms is the D1 is a bar and a D1 without a bar. So you could reduce this to D3 bar, D2 bar, D0 bar, and then a D1 bar or a D1. And remember, this one is always a 1. So you could reduce this to a 3 input from a 4 input. So you can slightly reduce this logic down to have less gates, or you can implement them with all of those gates for the 1 segment. So I thought it might be fun to kind of go through that, but we just don't have quite time for that.
Thank you.
See you guys. Requests for specific types of questions? Yes. So the truth tables, okay. So, okay. All right, so some combinational logic, yes.
Well, I don't know if that was just what I asked, but kind of creating an op-amp.
Okay, so the creating op-amp circuits? Okay. Any other requests? Oh, that's not good. Thanks.